I have to say at first, I haven't brought any props with me, so I'm very glad I've got Ian's duck to keep me company up here. Nor do I have anything to sell. Obviously, I've failed to prepare. However, in mitigation, I think I do have the best topic, because I think if we want to find life outside the Earth, the place to look is exoplanets. Exoplanets are planets which are orbiting around stars other than our own sun. Okay, so I'm going to start by setting the scene, and this is an artist's impression of our own Milky Way galaxy. I'm an astronomer, I work with light, and so I'm just wondering, so what we collect as astronomers is light using telescopes. So if we were to observe a galaxy like the Milky Way, what we would see is a lot of light, and that light is coming from stars. This is probably obvious, but I thought I'd say it anyway. Stars are much bigger and much brighter than planets. So as astronomers, it's fairly easy to study stars. Studying planets, which are not in our own solar system, is rather troublesome because they're small and they're dim, so they're difficult to study. The difference in brightness between the Earth and the Sun is a factor of about 10 billion. So you're looking for something very, very faint next to something much brighter. So that presents obvious problems. So I'm just going to tell you a little bit about stars that we're going to need later on. So this is probably the most important diagram in astronomy. This is the Hertzsprung-Russell diagram, and it's a graph of, on the y-axis, the brightness of stars, on the x-axis, the colour of stars. And almost all the stars in our galaxy that create that beautiful pattern of light that you saw in the artist's impression fall along the diagonal stripe up the middle of that diagram. And these are so-called main sequence stars. Our sun is an example of a main sequence star. And what all these stars have in common is that they're converting hydrogen to helium at their center, and this creates the energy that produces the sunlight and the starlight that creates light on the planets orbiting around the star. Our sun is about a third of the way up that stripe, and there are actually more stars lower down that are smaller, lower mass, fainter and redder. And then as you go up towards the top of that stripe, you've got more massive stars that are bluer and brighter. Okay, one of the things that we've learned in the last 20 years, which I think is really remarkable, is that we now know that there are actually more planets than stars in our galaxy. So when you look at the light in a galaxy, you see the starlight just because the stars are bright. But we've now done enough work on nearby stars in our own galaxy to know that actually, in general, stars do have planets orbiting around them. So there are lots and lots of planets in our galaxy. We don't know about all of them in detail. The assertion that I just made, that there are more planets than stars in the galaxy, is based on statistics. We know of about 2,000 planets in detail, and these have been studied by astronomers over the last 20 years or so. We know of 1,137 planetary systems, or at least we did on the 9th of September. So these numbers are about a month out of date. So we're probably up to about 2,000 planets now, because there's quite a large number of astronomers in the world who are constantly studying, looking for new planets, and there are new announcements coming out every day. So we know in detail of about 2,000 exoplanets orbiting around stars other than the sun. And so we now know that planets form with stars. There's no special requirement at all. 20 or, well, more than 20 years ago, it was possible still that our own solar system was unique. Something special had happened to the sun in its early history that created the material that then formed planets. But we now know that planets do generally form with stars. There's no special requirements. So we would expect the other stars, like the sun, to have planets also orbiting around them. Now, I should probably just tell you a little bit about how we found these almost 2,000 exoplanets that we know about, because I've told you that it's very difficult to see planets because they're dim. So both of the main ways that we've detected these planets depend on actually studying the light from the star and observing in the light from the star subtle effects due to the effect of the planet on the star. So you can actually, you think of planets orbiting around stars, but in fact, from the point of view of the laws of physics, both the star and the planet have mass, and they both orbit around their common center of gravity, which is much closer to the heavier star than it is to the light planet. So the star itself has a little orbit, which you can detect by looking at the light from the star and looking at the Doppler shift of that light. And then there's another even more simple way of detecting a planet around a star, which is if you happen to have a planetary system that's lined up so that the orbit of the planet happens to take the planet right in front of the star from our point of view, then the planet gets in the way and blocks some of the light. So you can actually see the star get dimmer every time a planet gets in front of it. So these are the two main ways that we've detected the almost 2,000 exoplanets that we know about. Okay, so I'm now going to change gear a little bit and go back to a brief history of life on the Earth. So I'm revisiting some of the points that Ian and Dave have already made. So from about 4 billion to 3.8 billion years ago, the Earth was being bombarded in an early period of its history called the Late Heavy Bombardment. So it was being bashed into by all sorts of stray bits of rock and asteroids that were chaotically orbiting around in the solar system. So at this point, the Earth was probably not habitable. But the interesting thing is, rather promptly, on astronomical timescales, a mere 300 million years after the Late Heavy Bombardment, we can see evidence that photosynthesis was already happening on the Earth. So that implies that life got started really very quickly after the Late Heavy Bombardment started. So this means that probably you don't require very special circumstances for life. Now, the rather more pessimistic thing is that complex life, of the sort of thing that you and I, trees, cats and dogs, that happened rather late. And this is at the very other extreme of the history of life on Earth. So it was about 600 million years ago that the first very complex life happened. So that may require rather special circumstances. So from analogy with that, it seems that probably life may be common on planets elsewhere in our galaxy, but complex life may be rather rare. Okay, so Dave told us that we need a source of energy and liquid water for life. And I told you about the different kinds of stars. Where you would need to put a planet in order to have liquid life on its surface depends on the type of star you're orbiting around. So the big hot blue stars have a habitable zone that's fairly large and fairly far away. The more plentiful, cool red stars are dimmer, and so you need a planet to be closer in to have a temperature consistent with liquid water. But it's more complicated than that. You can't just put the planet in the habitable zone and say it's going to be a habitable planet. It's much more complex than that. And as we know from our own solar system, the difference between Earth and Venus is dramatic. And it depends, a lot depends on the atmosphere and the clouds, whether you have a dry and toxic environment like Venus or a wet, habitable environment like the Earth. So clouds can help, as they do on Earth, but if you have too many clouds, they can trap heat and cause a runaway greenhouse effect. So it's really rather complicated to assess whether a planet is habitable or not. In the future, with more powerful telescopes, we may be able to make observations which will allow us to identify individual chemicals in the atmosphere of planets. And this gives us the potential to actually say, is there life now on the surface of this planet that we're observing? So, for example, on the Earth, we have oxygen in our atmosphere. Oxygen is highly reactive, and we only have oxygen in our atmosphere because it's being constantly replenished by the processes in plants on Earth. So if we were to be able to detect oxygen in the atmosphere of an exoplanet, that would be a so-called biomarker and give us a strong steer that perhaps there is, in fact, life on that planet. Now, finally, I'm going to, as promised, tell you a little bit about some work that we did here at the Open University. So I told you that most of the stars in the galaxy are along that diagonal stripe in this diagram. All of those stars will eventually run out of fuel, and almost all of them will end their lives as white dwarf stars, which are in the bottom corner of that diagram. And those stars are no longer doing nuclear reactions. They're just dying embers that are cooling like coals left over after a fire. And it turns out that planets can survive around compact stellar remnants like that. And surprisingly, the way that white dwarf stars cool actually leads to conditions where you could have habitable temperatures on planets for up to 8 billion years as the white dwarf is cooling. So we did a little bit of work just examining this using the real spectrum that you would expect from a white dwarf star. And we were able to calculate that if you put a planet in the right place, you could have this persistent habitable zone in which you have photosynthetically useful light that plants could use to generate energy, while simultaneously not having too much damaging UV radiation. So this is quite a sort of an optimistic, sort of very long-term picture that as all of the stars in the galaxy burn out, we could nonetheless have a galaxy that's teeming with life on planets around white dwarf stars. As we look sort of 10 billion, 20 billion years into the future, the prospects for life in the galaxy are actually rather promising.